We start solving this problem 77 of your textbook C Verma chapter rotation. Let's first study the problem, what they want to tell us. A solid sphere of mass m, phi, is released from rest. That means there was no initial velocity from the rim of a hemispherical cup so that it rolls along the surface. Here is the catch. It rolls along the surface. As I was telling you, in this chapter, you must be very careful to examine whether it is pure rolling or pure translational motion or both together. And as I say, if there are two motions together, you can analyze them separately and then just add the results. Additional of kinetic energy, additional of all these things you can do, add, right? So let us see, that is a hemispherical cup. Let me try to draw a hemispherical cup. No, here there is no hemisphere. So I have to draw it by hand only. So there is a hemispherical cup. Say this is a hemispherical cup. Fine. And there is a sphere. There is a sphere here. Now, the radius of this hemispherical cup is not known. The radius of the sphere is also not known. Only the mass of the sphere is known, small m. So we assume, say, radius of the cup is equal to capital R and radius of the sphere equal to small r. So when this ball starts rolling or the sphere starts rolling, at one point it will come here. If the rim of the sphere is kept horizontal, that means the cup is held right upward. Find the normal force exerted by the cup on the ball when the ball reaches the bottom of the cup. So when the ball reaches the bottom of the cup, the radius of the sphere cup is capital R, and this small ball, let me do one thing. Let me make this ball a little larger. Then it will be clear. This is the sphere. Its radius is R, and this ball is larger. Say its radius is smaller. The ball was here, and from here it started rolling down. It is clearly said it's rolled down. There is no translational motion. So we don't have to look after its translational motion. So when the ball comes down to the bottom of the cup, how much potential energy it has lost? We start from the energy. So potential energy lost by the sphere is equal to mg capital R minus small r. Very careful. It is not mgr because the center of mass is here. So the fall has happened from here to here, which is capital R minus small r. So this is the potential energy lost. So this will be the kinetic energy. This will be equal to its kinetic energy. This will be This will be equal to kinetic energy at the bottom. Let's find out some expression of the kinetic energy. Now, when the ball is rolling down, I make a picture here, a bigger picture of the ball of radius r. When the ball is rolling down with some angular velocity omega, then its center of mass has a linear velocity, and since it is rolling down, as I cautioned you earlier, here v equal to omega r relation holds good. V equal to omega r, because it is simply rolling down. V equal to omega. We use this concept. What is the kinetic energy at the bottom? Kinetic energy at the bottom is equal to, it will have rotational kinetic energy half I omega square plus the kinetic energy due to the translatory motion of the center of mass plus half m v square, where v is equal to omega r, omega smaller. This relation holds good because it is pure rolling. Let me write out, since pure rolling, this relation holds good. So this is equal to half moment of inertia of this solid sphere is 2 by 5 mr square by 5. This mass is the mass of the small sphere, 2 by 5 small r, 2 by 5 mr square plus, this is the moment of inertia, multiplied by omega square. Omega square is, omega is equal to v by r. So it is v square by r square plus half m v square. Here this 2 and 2 gets cancelled. This r square and r square gets cancelled. So we have 1 by 5 mv square and half mv square. 1 by 5 mv square plus half mv square is 7 by 5. 1 by 5 mv square is 1 by 5 mv square plus 1 by 2 mv square is equal to, you have 10 here, and here we have 2 plus 5, 7 mv square. So this is the kinetic energy. So this kinetic energy can now be equated with this loss of potential energy. So 7 by 10 mv square is equal to mg capital R minus small. From here again, m and m gets cancelled. So what we are left with is v square. So V square is equal to 10 by 7 G R minus R is 10 by 7 G into capital R minus small r. So this is one relation we got V square. Now, question is, what is the find the normal force? Normal, mind it, sorry, I forgot to mention this normal word normal here is not in the sense of normal means usual, not that. Normal here is perpendicular. Is a kind of perpendicular force. Now, when the ball is here, if you take the free body diagram of this ball and there is a cup, then downward force is mg and there is a upward reaction n. Also, yes, there is a centripetal force. So, N, there is a centripetal force. From here, we get that N minus mg is equal to the centripetal force. So, the normal reaction N minus mg is equal to centripetal force is equal to the centripetal force. And centripetal force we know is mv square by r. Therefore, so N is equal to mg plus the centripetal force. This normal reaction N they wanted us to find out is equal to mg plus what is the centripetal force by your earlier relation is mv square by radius. M is the small m. V square we have already got is 10 by 7 G into R minus R, and this divided by the radius of rotation. Here radius of rotation is capital R minus small r. That is capital R minus small r. So now what do we find? This capital R minus small r gets cancelled. So we have mg plus 10 mg by 7. So this is equal to mg plus 10 mg by 7. That is equal to 7 plus 10, 17. 17 by 7 mg. So this is the answer they want you to find out. So normal force, that means the perpendicular force that is applied by the bottom of the cup on the sphere when it reaches the bottom is 17 by 7 mg. Okay? It was not a very large problem, but you need to just understand what the problem